Alright, so this topic is the first of improper integrals, and what we mean by improper integrals, there are basically two types, and the first type is integrals that have, well, essentially the limits of integration are at infinity. And so if you remember the geometric interpretation of an integral, the integral from a to b of f of x dx geometrically, as we know, corresponds to, you're looking at the graph of the function in the interval from a to b, and you're trying to calculate that area. Geometrically gives the area of this region over here. And so the first idea is that if the limits of integration are infinity, so by the limits of integration we mean, if that or that, if one of these is like infinity, and so then geometrically you're imagining a situation where, well, the graph maybe goes on forever, and you're trying to calculate the area of this shape. So for example, if the integral is from a to infinity, then you'd want to know the area underneath the graph of the curve going from a but out forever. And so that's kind of a strange idea because when you think of like the area of a rectangle, it's space times height, and so if like the base is infinite, you would think that there's no possible way that the area could be finite. Turns out to not always be the case. But anyway, so that's the idea of what we mean by improper integrals with limits at infinity. Okay, so first let's just introduce the formal definition of what we mean by this. So the first thing is we're considering integrals like of this form. So integral from a to infinity of some function f of x dx. So, and how is that defined? Well, to define it, we just define it using a limit. So it's just the limit as b goes to infinity of the ordinary definite integral from a to b of f of x dx. So that's formally how you define taking a integral where the limit of integration here is an infinity. So it is you can argue it's sort of like a definite integral because it has these endpoints, but we refer to it as an improper integral because, again, the limit is infinity. So that's how you define it. So you're just taking the limit as a goes to higher and higher values of b here. Anyways, so that's how you define it, like that. Similarly, if the lower limit could be like negative infinity, so you can imagine how you would define that. So like negative infinity up to b of f of x dx. Well, how do we define that? Well, you can imagine how we define that. Now it's going to be the limit as a goes to negative infinity for the integral from a to b of f of x dx. So that's how we define this type of improper integral. And then we can combine them using the fact that like areas add or over regions, which gives us one of our properties of integrals. So now that we know how this is defined, we can even talk about integrating something from negative infinity up to positive infinity. And we can just define that by, well, you can pick anything you want, but it would just be, essentially, you can just define that to be the integral from like minus infinity to anything of f of x dx plus the integral from that same anything to positive infinity f of x dx, just using this property of integrals. So in identification 3, we're using this general property of integrals, so like the integral from a to b of f of x dx plus the integral from b to c of f of x dx. Same function, adding them, and you want these, you want this upper bound here to match with that lower bound. Then one of the properties of integration, of definite integrals, says that they, sorry, that should be a c. That's the integral from f of x to c. So we're sort of using this general property. We're now, yeah. Anyways, so that's where condition 3 comes from. So let's have a look at these one more time. So these are just the formal definitions of how we calculate these definite integrals. And